Welcome to this lecture number 2 on the basics of control systems for the course on electric vehicles. My name is Ramkrishna. I am a professor of electrical engineering at IIT Madras. So, in this lecture, we will look at system performance or how a system evolves with time. Specifically, how does the output of a system vary with time. As a simple example, you can look at what happens when I switch on an air conditioner, right? It does not cool off or cool down the room immediately. If I switch on a fan, it takes some time for the fan to attain its top speed. If I am in a car, it does not go from instantaneously from 0 to 60 kilometers an hour. There is some time lapse between it going from 0 to 60 kilometers per hour, right. So, in this lecture, we will look at what are the various ways of analyzing system responses. We look at what is called as a natural response and also the forced response, or largely classified as also as a transient and a steady state response. And for the complete response of the system, for example, how a fan works, I should know how long it takes from 0 speed to attain its full speed, right, and what happens in that process between I switch on the fan till it goes to its full speed and so on. So, a complete response of the system is given both by its transient and steady state responses. As a simple example, we can also look at this as an example of a ceiling fan, which can be modeled as a simple RL circuit. I just look at the differential equation. It's a first order differential equation. There is no external voltage source, and let's say that initial current is 5. Or if I look at in case of a fan, let's say it is revolving at certain speed, right, and then I switch it off. Right, when I switch it off, the fan has a certain speed. Let me call that speed as something corresponding to 5, and we say that eventually the fan goes to its 0 speed. This is a natural response, right? If I just leave something from an initial condition, it will go to its 0 condition. If it starts at 0, it will be at 0. If I switch on this air conditioner in this room, it will go back to its natural temperature, which could be slightly higher than what I see now. Maybe it's now 21. It might be 28 or 32 depending on the ambient weather conditions. On the other hand, if I want to switch on a fan, which means I put a 20 volt source, let me call this at 20 volt at say some t equal to 0, okay, then what happens is just that the current builds up, the fan does not go to its full speed instantaneously. A bulb is a little different. I switch on a bulb, it just glows full brightness because it is just a resistive circuit, it is just of the form V equal to IR. Now, I have a V equal to IR plus L di by dt. There is a differential equation or a differential term involved here. And if I solve this, this just has a form of the I forced. The reason I use forced here is I am pumping it through an external source. There is an external voltage source, right? And at t equal to 0, I solve this, I get at t equal to 0, this becomes 1, the current is 0, therefore, the speed is 0. And as t becomes very large, I look at limit of this I as t goes to infinity, V 0 by R 1 minus e power minus R by L t. This becomes just V 0 by R. Okay, that is the value here. What is V 0 here? 20, R is 10, V 0 by R is 2. Okay. So, this is the forced response of a system. Natural response, what happens when there is a non-zero initial condition? The system comes to rest. Forced response, system starts from a 0 initial condition and it attains its full speed at the steady state. Okay, it need not necessarily start from 0, it can also start from a condition maybe which is somewhere here, and or even initial speed of something, it will reach to its final speed in a stipulated amount of time. Okay, so this, I know two things now. What happens to when the system is just subject to an initial condition, there is no external influence, the system goes to 0 state. If I switch on or give a voltage source, the system goes to some steady state value. Okay. Now, in most cases, I do not know what are the inputs prior to design a control system. However, to analyze the performance of a control system, it is useful to know what happens to the system when subject to standard test signals. One test signal is the initial condition, which we call an impulse. Maybe I just take the fan, I just perturb it a little bit and leave it, just maybe slowly rotate and then come back to its speed, right. So, I would like to therefore know what happens when I subject this to a standard test signal. So, in general, how do I specify a system, right? I am interested in how fast my system goes from 0 speed to the steady speed, or if I switch it off, I want to know how fast my system goes from certain speed to a 0 speed, right. So, the standard signals will include a unit impulse, which in our case means that the system is a non-zero initial condition. A unit step, sudden change, like I am 0 volt till 4 volt, or even if you look at a fan which has a regulator which goes from say 0, 1, 2, 3, 4, you go from 0 to 1, that is a step change. Say it is at 1 for a while, then you switch it to 2. This is a sudden change. Then you have a ramp which is a constantly increasing voltage, say voltage of 0, 1, 2, 3, 4 and so on, or a parabolic acceleration, or also inputs could be sinusoidal, right, V equal to V0 sin omega t kind of. And these inputs are captured because most of the variations that you see in life or in real world which largely be captured by this 1, 2, 3, 4 and 5 signals. Okay, how do they look like? So, this is my unit step. This is the ramp which is steadily increasing and a parabolic input. Okay, so if I look at a first order system, when I say first order means in my language it would mean just one pole for the system. I have something called a system time constant, right. A system is denoted by its time constant, characterized, and this will have a lot of useful information for the system. I start with a system which has a reference signal, which has an output, and what I want is y of s should go or should track r of s in the steady state. Okay, now what does this number do, right? So, let us take two examples here. Let us say a sports car takes around 3 seconds, right. So, if I say I model this car as something like this with the time constant t as or tau as 0.5. Okay. Now, if I say okay, I give a reference of 100, okay, or I want it to go from 0 to 100, what happens? So, I look at the output speed. I have so if y of s is u over 0.5 s plus 1, I look at the inverse Laplace transform. So, to find what is u of t, its response looks something like this. So, what happens here is that we see that the system goes from 0 to 100 in about 3 seconds. Okay, so what else can we do? So, now suppose I change t from 0.5 to 2. Now, what I see, the same analysis I do, and what I get is the system goes from 0 to 100 now in 12 seconds, right. So, this tau, which is a time constant, decides how fast my system responds to input. The higher the time constant, slower the response, and vice versa. Higher the time constant was 2, slower is the response. A smaller time constant will give me a faster response, and therefore, this can be chosen as a design parameter of how fast I want my system to attain the steady state, or how fast I want my system to go from 0 to a certain speed, right. And this is a little comparative thing of what happens for tau equal to 0.2 till tau equal to 0.6 and so on. Okay, so that was for first order systems. We will also look at second order systems which has like 2 poles of the system. So, we can look at examples of this as a simple say RLC circuit. I think we had derived some transfer function in the previous class. I have a R, L, RLC circuit, a V, a R, L and a C. So, this will constitute a second order system, right. I think we did derive a transfer function of this. So, if I just look at V over I, this will have some pattern which looks like this. So, bunch of things I have here. So, omega n I will call as the natural frequency of the system, zeta is a damping ratio and so on. So, if I look at what are the poles of the system, the poles of the system are just I equate this denominator to 0, and now I am just solving a quadratic equation. Okay, so quadratic equation will have two roots of this form, and based on the value of zeta, right, the system can have roots which are distinct and real and negative. So, the poles will always be negative in this. So, poles will always be in the left half plane, or at best it will be on the imaginary axis, right, based on because of the structure of this. Okay, now zeta is greater than 1, I will have two distinct negative poles. So, my poles will be somewhere here and then somewhere here. Zeta equal to 1, I will have just some repeated roots at omega equal to at s equal to omega n. Under damped systems, then under damped system is zeta being between 0 and 1. This thing goes negative, and therefore the square root will become imaginary and so on, and I will have roots which are complex and conjugate. And purely or system which has no damping will just be an underdamped, and the roots or the poles will be purely imaginary in nature. Okay, so we will be interested in looking at how each of these systems for different zeta will react to a step input, right, in a way of what happens when I apply, say, a voltage of 20 volts to this RLC circuits. And I think we would have done this in our circuits course, if you do not remember, in controls course. We looked at several kinds of damping of underdamped, overdamped, critically damped and undamped and so on. An undamped circuit here would mean for 0 voltage would just mean that I am looking at pure a simple oscillator, or the harmonic oscillator as we call it. And so, this is zeta equal to 0 and without any external voltage. Okay, so in the underdamped case, and the reason I call it underdamped is because the system wants to go, I want the system to go from 0 to 1. Okay. So, in the first order case, what we saw was that if I wanted the system to go from here till here, I just did something like this, right, it was just right. Here what happens is, given the nature of this, again I will not go into where this comes from. This comes from largely from looking at the inverse Laplace transform of 1 over s omega n square over s square plus 2 zeta omega n s plus omega n square for complex roots. For complex roots, my solution will be of some form, I think something like 1 minus e power some exponential and then some cosine term and so on. So, not exactly like this, but something around this. Okay. So, several things can happen. So, I look at zeta is 0.1, which is this one. I have zeta as 0.3 somewhere here, zeta as 0.5 which is somewhere here, zeta as 0.707 which is here, and as I keep on increasing zeta, so this is the zeta equal to 1 line, this is the zeta greater than 1 line. Okay, so what is the observation here? The observation here is that, okay, for let us say I am looking at zeta is less than 1 and greater than 0. Those are values which is here, and also which is here. Okay, these three values. In these three values, what I see is that my system starts at 0, it goes to some value above 1. Here it is like close to 1.7, here I have something like 1.4, 1.2 and so on. Okay. Now, these here also there is a small overshoot here, right. So, these things when I go from, so this is my desired, and this is where the system takes me. So, this is called the overshoot, okay, and the system will keep oscillating until it reaches a steady state, okay. And then how much is the overshoot depends on how much is the damping, okay. Now if I look at zeta equal to 1, critical damping, it just starts from here, it just goes and settles down here. For larger zeta, its response is much slower. And what is zeta? Zeta corresponds to my damping. Okay, and it's kind of intuitive to see, right? More the damping, slower will be the response. So, if I want a faster response, I experience an overshoot. If I want a slower response, well, I will just maybe, if I don't want an overshoot, I will go for a slower response. So, what are the cases where I can design the system for to be over damped or even under damped? Say, for example, I want my speed to go from 0 to 60. Okay. So, will I go like this, because everybody wants to go fast, right, or will I go like this? Okay. And if I want to go from 0 to 60, maybe I can go till 66 and come back and then slowly try to accelerate. I just put my pedal in such a way that I first overshoot 60 and then I come back and so on, right. Of course, that I do like a little adaptively when I pedal or when I drive my own car. But in general, it is allowed to go above 60, come down to maybe 54 and slowly settle down, right, because I want a faster response, right. Now, similarly, if I do an air conditioner, right, I am allowed to have a faster response. I really want the temperature to go down to my, so outside is 42 degrees, I come inside, it's like boiling hot, I switch on the AC, I want it to go down very fast. And say my set point is 21, right, it is allowed for it to go to say 21 or even 20 or 19 and then settle down eventually to 21. Okay. Whereas, if I am on a elevator, so to speak, say I want to go from 0 to the 10th floor, but I would not want it to go from 0 to say 10.5 and then come to 9.7 and slowly settle down. That's not a good design. But in an elevator, it just goes and then slowly settles down to the floor that you want to reach. So, depending on the application at hand, depending on how fast you want the system to respond, you will design your system to either be under damped, over damped, or even critically damped. So, when zeta equal to 0, when there is no damping, the system will just oscillate like a harmonic oscillator or a simple pendulum without damping and so on. So, different responses. So, for zeta equal to 1, the system just goes and slowly settles down, and as I keep on increasing the zeta, the system becomes slower and slower. So, zeta increases, the response is decreases in the way that the response gets slower and slower, until a case where you have infinite damping, the system will never move. Okay, now based on this, we said, okay, should we want the system to be faster, should we want it to be slower, how much of the overshoot I will allow, and so on. It is good at some point of time to quantify what is happening here, especially in the case of under damped systems. What we saw is that my system goes to fairly large values. It starts from, it has to settle down at 1, but it goes to 1.7, 1.8. Say suppose I want my current to settle down at say 5 amperes, but what if it goes till 8 amperes? Will my insulation or will my physical capability of the wire allow that, right? So, at what is the trade off between having a faster response and also having the system safety, right? So, we will quantify this as few things now, right? So, as the rise time, the settling time, the overshoot, and so on. So, typical response is of this form. So, I will have the rise time is the time where I reach 90% of the steady state value. Again, these are of interest only in the under damped case, because in the over damped and critically damped we do not have an overshoot. Okay, so then I have the peak time, the time where it reaches the maximum value. At this peak time, I have a certain overshoot. If this is 1, this is 1.5, then I call it as a 50% overshoot. And this overshoot I measure in percentages. Then I have the settling time. How fast do I reach within the vicinity of say 60 kilometers per hour or 21 degrees Celsius in the room, right. So, you can define it as the first point when I reach within 2% of the final value or within 5% of the value, and these are typically given by these numbers, right. So, again I will not do the math of this, you possibly would have done in other courses, or I will give you some material, but let us observe these numbers carefully, or these quantities carefully, if not numbers. So, I look at the peak overshoot. MP depends on zeta, okay, and then if I increase the zeta, it reduces the peak overshoot, Okay, so I was going, say my current was rating was 5 amperes, I go to 8 and then oscillate. Well, now I am going to say 6, which means I increase the zeta. But when I increase the zeta, my settling time also reduces. Right, so that is a little trade off, right? So, and also if you could see those from the comparative plots as well, of what happens to the settling time and so on. Okay, so increasing zeta reduces the peak overshoot, but also increases the uh, oh sorry, I think. Okay, let us quantify each of these things. Let's see what we observe. We observe that the system starts from 0, it reaches a peak and then slowly settles down. So, we will define few quantities here. We will define the rise time as a time it takes to reach 0.9 of the steady state value. We define the peak time as a time where it reaches the maximum value. At the maximum value, I overshoot my steady state value. So, this will be called the peak overshoot. If MP is 1.5, I will call this as a 50% overshoot, which means that and I will measure this in percentages. Settling time is how fast do I reach within the vicinity of my steady state, 60 kilometers per hour or 24 degrees or 21 degrees and so on. So, I define it in two ways, at 2% of the final value or 5% of the final value. Okay, let us look at each of these quantities now. Look at the peak overshoot. The peak overshoot depends only on the damping ratio. Okay, and what we also see is that increasing zeta reduces the overshoot. That's what we saw in this pictures here. I increase the zeta. 0.1 has the highest overshoot, and then say 0.707 has the lowest overshoot. So, increasing zeta reduces MP. Okay, but it may reduce the rise time. What is the rise time? You see that the response becomes a little slower. Let's say if so, it takes some time to reach to the 90%. It takes a little more time, and so on. But that's okay. That's what kind of trade-off that you are looking for. And increasing the zeta, if the denominator increases, the numerator also does. So, it also has a good effect on the settling time. So, for a smaller zeta, which means this is less damping or lesser damping, and the system will therefore be more oscillatory in nature. Okay. So, while designing a system now, given specifications, I can now choose what is zeta, I can choose also what is omega. These are parameters that I can choose, right. In my RLC circuit, I can choose R, L and C to have a certain value of zeta and a certain value of omega n. Okay. So, a very small example in this direction. So, I just give a transfer function and I want to find out what is zeta and what is omega n, and therefore, what is the peak overshoot, the settling time and the peak time and so on. So, based on this structure, I can identify say I just compare this and this, my omega n will be 10, zeta will be 0.5, and for zeta being 0.5, I experience an overshoot of 16.3%, a settling time of 0.8 seconds and a peak time of 0.36 seconds. Again, the response will be something like very similar like this. Okay, so where the overshoot will just be about 16%. Okay, so why do we do this, right? What is the most motivation to do this? So, typical performance specifications often involve requirements which are associated with how fast or how slow the system responds, how system responds to a certain input. Okay, and then this time domain specifications, we define them as the rise time, overshoot and so on. it gives some insights on how system responds to what are the transients, how it responds to a step change, and so on. Okay. So, what does the rise time tell you? The rise time tells how fast a system responds, or they measure how fast a system responds and also how fast a system stabilizes. Overshoot is used to assess stability and also safety margins, right. So, if my current or if my system is rated for 5 amperes, if it can take 8 amperes, then good, I can design it for that level of overshoot. But if it cannot, I will maybe design it only for 6 amperes, or even in the worst case I can only design it to be overdamped system. So, too much overshoot can indicate instability or even physical instability, or even may damage the system. And settling time provides how long it takes for a system to converge to a steady state after a disturbance, after an initial condition, or even after being subject to some kind of input. Okay. So, what we have done so far is to look at this part of this, right. So, what happens if I go further in time, what happens here? That is called as the steady state response. Okay. So, a natural question is, what happens after all the transients die out? Does the system output reach the desired reference, or does it maybe fall short? Okay. So, we will do a little analysis on this. So, what I look at the transient, if I look at the expressions that I had earlier, V0 by R 1 over e power minus say some say R t by L and things like that. So, I'll maybe go back to the circuits and tell what is the difference between the transients and the steady state. So, in this, this is the transients, and the steady state is what is left after the transients die out. So, how do I mathematically say it? Mathematically, I will say what is the limit as t going to infinity I L of t. In this case, this would be I L 0, which is 5 e power minus R t by L, all this as limit t goes to infinity, right. And I know that e power minus infinity it tends to 0, so this will be 0. So, steady state here is 0, that is what the picture also says, yeah, this is 0, right. And then same thing here, what happens after the transients died out? Transients are all the terms which have a t in them, if loosely speaking, right, if you were to distinguish between transients and steady state. Now, steady state here is V0 by R. So, these are all the transients until here somewhere I am around at the transients, and then I reach to the steady state. And how fast or slow I reach depends on the system parameters, the time constants, the zeta, the omega, and so on. Okay. So, now what happens at steady state? Does it actually reach say 60 kilometers per hour, or does it fall short of 60 kilometers per hour? And it's also, its value of course depends on what is the type of input, what am I tracking, and so on. And also the number of integrators, right. Okay, this is a little complicated word for now, but we will try to resolve it. Okay, let me say that I have so we'll try to derive whatever is in this table. So, let me open the writing pad. Say g of s is 1 over s tau plus 1, or we say, okay, okay, let me say that g of s is now say some number k over s plus a. Now, what is my steady state error? Steady state error is for a step, the steady state error is limit s going to 0, 1 over 1 plus g of s, that is k over S plus A. Let me call, say, let's say A B equal to 2, just for simplicity. Okay, so this will be S plus 2 over S plus 2 plus K, limit S going to 0. So this will be 1 over K. So if the reference is a unit step, then the steady state error is 1 over, say, some K. Maybe this is a variable, right? Okay, now how do I reduce the steady state error? I can increase K and reduce the steady state error. Can I make it to 0? The answer is no, because I cannot really increase K infinitely to arbitrarily large numbers. Okay, so if I see a little picture of this, this is what it means, right? So let us say K equal to 1. So this, so maybe say, okay, so K sits here, let us say K equal to 9. GS is something like this. The error at t equal to 0, y is 0, so the error will be 1, and then the error goes down slowly till 0.1. The output also goes, so this is what happens to the control input. The control input starts at 9 and then goes on till 1. What happens to the output? So this error is 0.1, so the output should only be 0.9. So this is the steady state error. With the steady state error of 0.1, that is what we check here, right? So E of t plus y of t will give me the R of t. So that is kind of nice that is happening here. Okay, now what if say G of S is of the form K over S plus 2. Okay, then limit the steady state error is limit S tends to 0, 1 over 1 plus K over S plus 2. So this will be S plus 2 over S plus 2 plus K. This will become 0, right? So if I add a pole here at the origin, so a pole at the origin and RS is a step, will mean that the steady state error is 0, right? I can maybe just see how the picture of this looks like. Okay, so I have a pole at the origin for G of S, so I am just multiplying these two, I call it G of S. The error starts from, as usual, 1, it oscillates a little bit and then error goes to 0. My output goes 0 to 1 with a small overshoot, which again I can look at as a design parameter. We will slowly see what happens when there are disturbances, right. So, two examples I showed you. One is a plant of this form and then a plant of this form when there is a pole at the origin, right. So, here there is a constant steady state error. In the picture we saw the error was 0.1 and increasing gain K will reduce the error. So, this we will also call as a proportional controller. Proportional control. Okay. But if I just add a S here in the denominator, my error goes to 0. This is called integral control. Okay. Similarly, I can look at other signals also. Okay, I'll do one more and then we will the rest I will leave as an exercise. Now let's say my R of S is 1 over S square. Okay, this is like a ramp, a unit ramp. And let's say G of S is as usual K over S plus 2. Steady state error. Now for a unit ramp, I'll just look at, so what was my, I start from the definition. E of S over R of S was 1 over 1 plus g. When r is 1 over s square, my E of s becomes 1 over 1 plus g times 1 over s square. And now I look at the steady state error, limit s going to 0, s times E of s. For this case, again it is easy to verify, will become infinity. Right. So, this is a case where I have a plant of this form, the reference is a unit ramp and the steady state error is infinity. If I just draw, so this is how my unit ramp will look like, and my system will be such that the error just keeps on going unbounded like this. The error just increases with time and becomes infinity. Okay. So, to summarize, there are different kinds of signals that I would look at here. That is, so I look at the number of integrators in g of s, which, so if I say g of s has one integrator or two integrators and so on. So, in this first example, this g of s has 0 integrators. In the previous case that we saw, here g of s has one integrator and so on. So, typically g of s can be something like 1 over s power n g prime of s, and this n is the number of integrators, and similar computations will tell me that, okay, for a type 0 system, when there are 0 integrators, I will have that for a step input there is a certain error. Again, for a type 0 system, if the input is a ramp, the steady state error goes to infinity. Similarly, for a parabolic input also, the steady state error will go to infinity. If I have a type 1 system, which is the example that we worked, when the input is a unit step, I have a 0 error. For a unit ramp, I will have a constant error, infinity, and so on and so forth. Okay. So, in this example, this is again easy to work out, something similar we had worked out. I will have a 0 steady state error for a step input. I will have a error of 1 over 10 for a ramp input, and so on. Okay. So, what are the features of the steady state error now? The steady state error is a measure of the system's accuracy, right. In an ideal scenario, the output should go to the reference as close as possible, or it should directly match the input with time. It means the steady state error should be 0. If not 0, it should be as low as possible, right. And it depends on two factors. It depends on what is the reference and how my plant actually is, how many are the number of integrators in the plant, right. And of course, the steady state errors I will calculate only for closed loop system. For open loop system, the quantity may not be very well defined. So, to summarize, we started off so far with the control philosophy. We asked ourselves certain questions, and to answer those questions, we wanted to refer or represent the system as certain transfer functions or differential equations and so on. And then the questions we asked, how does the system respond to certain inputs? And then we devised for ourselves what is called the transient response and the steady state response. And both of these, transient and steady state, will now form the backbone for any of the control design that we will see in the upcoming lecture. Thank you for listening.